had Charlie working, I guess, three sort of separate but related areas. First of all, just as a warm-up, I had him. I asked him to start looking at light curves, and the light curves we looked at were based on the data obtained by the All Sky Automated Survey for Supernova, and that's a system that basically observes the entire sky every night, all clear nights, and basically detects and records the brightness for every star that's detected in the images. Now, that program is primarily interested in looking for supernova, and they're very successful. Over 1,000 supernova this program has detected, but they also detect and measure every other star that's detected in their images. And they go to the trouble of recording and documenting the light curves. Now, they have developed automated systems for classifying those light curves, but they realized that, sometimes that sophisticated artificial intelligence system that they developed just wasn't all that good. And that sometimes the best way to do it is to have a human actually look at the light curves and do the classifications. So that's one of the tasks that I suggested that Charlie start doing. And it's sort of a good introduction to light curves. And so that was a good start. The second part, secondly, I asked him to look in particular at light curves for Cepheids. Look at the light curves that have been recorded for Cepheid variables, but in particular, light curves are normally very smooth and well-defined, but sometimes Cepheid light curves have bumps. They have bumps in them. And I suggested that Charlie look for Cepheid light curves that have bumps and document and record which ones have bumps, where they actually occur. This is something that hasn't, as far as I know, hasn't really been done that much at all. I mean, and thirdly, that was data that somebody else was taking. The third part of what I asked Charlie to get to work on was to actually take his own data with using our robotic telescope, GORT. And I suggested that Charlie look at 2 target objects and accumulate data and generate his own light curves, not light curves that were created by somebody else. And I'm going to turn it over to Charlie now. But first, I want to say, when I first met Charlie, I asked him, I said, well, do you know about spreadsheets? Do you know how to use spreadsheets? And my memory is that he said, well, not really, but I'm a fast learner. Well, he was a really fast learner and ended up doing a phenomenal job for somebody who didn't know how to do much with spreadsheets when he started the summer. So, Charlie, are you there?
Yeah, I am. So I'll present my presentation. Okay, so this is my an internship presentation on observing different stars and light curves. So first off, one of my first tasks was to look at this website called ASSN, where they took light curves from a bunch of stars. Light curves is a measurement of a star's brightness over time and how it changes. So using that information, we can tell if there are objects orbiting stars. So we looked at light curves and we determined the classification. There's four-ish different classifications for stars. There are rotational variables, eclipsing binaries, pulsating variables, and unknown variables. So this is an example of a rotational variable. So a rotational variable is just when there is an object orbiting a orbiting a star, so it makes the star's brightness go up and down pretty evenly. This is an example of an eclipsing binary, a light curve for an eclipsing binary. Eclipsing binary is when there's a star, but then there's something of pretty equal-ish size going around the star. So that it eclipses it, and that's what that big dip in the light curve is. And then there is a pulsating variable, where a pulsating variable is not really caused by something orbiting the star, but it's caused by something within the star, like the star just changing its brightness. And that kind of creates a sort of wave-ish. I mean, there's other like light curves, but like it's mostly like a lot of like ones that kind of look like a wave. And then there's also unknown variables, where for me, unknown variables just don't really fit into any of the categories. So something that I personally kind of struggled with was figuring out the difference between an unknown variable and just something that's junk. But unknown variables, they don't really fit in with the other ones. So they're not really you flag them as unknown variables, which is, and then the people who are running the ASSN website take a look back at it and look at it. So I put all my information down on a spreadsheet, and then here's a graph from that information based on the spreadsheet. Something that I found a lot of were eclipsing binaries and pulsating variables. So a conclusion that I've drawn from this is that there are just eclipsing binaries seem to be very common. Like eclipsing binaries and pulsating variables seem to be very common. Seem to be pretty common. I found exactly 100 eclipsing binaries. So that's definitely one of the largest amount of stars that I found in my research. Another thing that I was working on over the summer was looking at Cepheid bumps. So Cephids are a type of pulsating variable. They so there's different within those like 3-ish types. There are like little subtypes, and so one of the subtypes for pulsating variables is Cephids. So sometimes the Cephids have bumps. This is an example of a Cephid bump, where it goes up and then it goes down again, and then it goes up a little again for a bump, and then it goes back down. And then this is an example of regular Cephid. There's, as you can see, that it just goes down, up, and then back down again. No like bump or anything. I put this into a spreadsheet again, and then here's another graph from my information on the spreadsheet. I didn't find a lot of bumps. I found 104 that were not bumps, 42 that were bumps, and then there's one that I was a bit confused on, and so I had that there, and I didn't take it out. But for like what I've concluded from this is that there tend to be more Cephids that have bumps than Cephids that don't. From what I remember, we don't really know a reason why some Cephids have bumps and some Cephids don't. But it was interesting to look through and see like the kind of the ratio of which ones do have bumps to which ones don't. And then another thing that I worked on was I was looking at the SAR SS Cygni. We used the telescope GORT to observe the star SS Cygni. And so we got images of SS Cygni, and then we analyzed those to figure out the brightness levels of the star at different periods. And then I made my own light curve based off of the information that I gained. And so during the time that I was looking at SS Cygni, it didn't seem to be doing a lot. There was a period where I got really high. I got really high relative brightness compared to the other ones, but I'm pretty sure that was due to a satellite or some clouds getting in the way. And then I was also looking at HO vol. It didn't seem to be doing much either. I didn't study it for as long as SS Cygni, so I wasn't able to get as much data points as I were for SS Cygni. But for the data points that I was able to get, HO vol didn't seem to be doing much. Thank you for watching my presentation.
Okay, well, thank you very much, Charlie. Let's give Charlie a round of Zoom applause.